Hi everybody, this is lecture number 29 from our statics class, and we've covered almost all of section 7, so today is going to be the last lecture that we cover on chapter 7, and it's actually a way that we're going to start talking about the things that we've done, the load, shear, and bending moment diagrams, mathematically. So far our solution has been a graphical solution, so we're now going to take a look at what these look like in terms of math. All right, so whenever we do shear and bending moment diagrams, we always stack 3 diagrams. We first of all do the free body diagram showing the loads, and then directly underneath it we show the shear diagram, and underneath that we show the bending moment diagram. Well, it turns out that there's a pretty good mathematical relationship. And if you have a curve, especially that is irregular, like this W or load per foot curve, load per foot relationship is not linear, but it would be some sort of a function of x. It turns out that the shear at point D, or any point, minus the shear at point C, is going to be equal to the negative of the area under that load curve, which is the definite integral, the negative of the definite integral of w dx. So if w is given as a function of x, you can put that in here and then integrate that between those limits. Once again, it's always a definite integral to find the difference. So if you knew v at d, you could take this quantity, this integral quantity, subtract it from the shear at c, and you would see what the endpoint looked like. Now similarly, when you have the moment at point D and the moment at point C, if you have shear as a function of x, you can integrate that, and it's not the negative, but it's the positive just because of that sign convention that we talked of, or exactly the area under the shear curve. So the difference in moments between 2 points is the area under the shear curve, and the distance in shear between 2 points is the area under the load curve. Now, this can be very, very helpful. Like I said, if omega or v, or excuse me, if w or v is given as a function. So if it's not given as a function, then using purely graphical solutions is a good idea. If it's given as a function, sometimes using purely mathematical relationships is a good idea, but a lot of times you can just use this information to assist you as you're doing a graphical solution. So anyway, if we continue along that train of thought, there we go. So we can take a look at our reactions here. This is just the relationship thing again. This is, and we're only doing from slide 22 to 29 on this, and then that will be the end of our discussion. But if you have some kind of a W, which here we know the reactions at A and B, and you can see that the shear curve, that V, is actually a straight line, right? We can find the slope, we can find the intercept, and we can set that up, and then we can find out maximum. What this also tells us is that where V is 0, M is going to be a maximum, which is what we already know from calculus, that that those two values are going to correspond to each other, a maximum or a minimum. But mathematically, if it's parabolic, it's going to be at the top or the bottom of the parabola. All right, so here's just an example of using this material to solve this type of an equation where we have 2 point loads and a distributed load, an overhanging beam, and 2 supports. All right, so we can start by doing our moments and finding those reactions at A and D. And then we can do the dv dx equals negative w, or this is the mathematical equivalent of dv is equal to negative w dx, and then integrating both sides. Definite integrals, always. Right. So if we use that, we can see that mb to ma, we can see what those values are, mc to mb, mb, and so forth. So we can draw this odd moment curve mathematically. Every time that there is a change in the loading situation, you need to find a new point. Then you can determine if the relationship between those points is straight line, parabolic, or some other function. All right, so here's a cantilever beam, same sort of an idea, where we want to find the shear between point A and point B, right? So once again, we want to do some statics, find out what's going on, and then since this is a straight line, when we take VB minus VA, we can relate that, but we know since this is a straight line, this is going to be parabolic. And you can see that also because when you do the functions, you'll get an a squared term, which indicates that you have not a straight line, but a parabolic function at that point. All right, so then from here to here, since this has a slope of 0, this is going to be a straight line. So the moment, we can find the beginning and the end point, and we know what the function looks like. Same thing here, beginning and end point, and we know what the function looks like. And between those two things, we are able to determine what that load curve is going to be. Load curve, excuse me, shear curve, and moment curve. All right, everybody, so that's it for Chapter 7. I will post 1 or 2 more homework problems. That'll be it. When we come back on Monday, we have 1 more week. We're going to talk about friction, and then we'll have 3 days on friction, 1 day as a review for the final exam, and then the final exam. Thanks. Have a great day.